Welcome to this presentation, Challenges of Intrusion Detection Systems in the Cloud. This is being recorded for ICTN6870 in the spring of 2015. My name is Milton Koger. So our agenda for today, I'll provide a brief introduction to the topic. We'll discuss what the problem is that we're trying to solve, why is it important. We'll discuss some research methods that have been applied to address these questions. Then we'll talk about the findings of those researchers, and we'll discuss what their findings tell us and what conclusions can we draw from those findings. And then finally, we'll go over the references that we use as the sources for this presentation. So the first question we might ask is, why is the cloud different? Well, the National Institutes of Standards and Technology, or NIST, has defined cloud computing as a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources, such as networks, servers, storage, applications, and services. So one of the important considerations there is the idea of dynamically allotted resource pools, where individual virtual hosts come and go. So, as you might imagine, that provides particular challenges to intrusion detection and intrusion prevention scenarios, such as questions of attribution, who did what when, data remnants. When we release resources back to the pool, will subsequent users of that storage, for example, be able to see data that we had written to it? Or is that storage forensically speaking cleared before it's reallocated? And then we've also got to worry about insider attacks between virtual machines. There have been some well-documented cases of subscribers to Amazon's Elastic Compute services, for example, using virtual machines in that environment to attack other virtual machines hosted in that environment. The Cloud Security Alliance is a consortium of cloud service providers that have proposed guidelines, recommendations for the use of cloud services, and they also offer a certification actually for cloud security. And this alliance has proposed several controls, but all of those controls are primarily process-based or administrative in nature. So they rely on people following the rules. Obviously, bad actors aren't going to follow the rules. Another challenge that I face in my day job is for federal information systems. All .gov systems fall under the requirements of the Federal Information Security Management Act of 2002, or FISMA, which requires over 200 controls to be implemented, including multi-factor authentication for remote access, continuous monitoring, intrusion detection, periodic vulnerability scans, media access control, etc. So you can imagine that meeting those requirements in a cloud environment can be additionally challenging. So what is the problem we're trying to solve? Well, the Cloud Security Alliance recommends that we run intrusion detection systems in our cloud environments, and FISMA actually requires that we have intrusion detection systems. These systems are traditionally either host-based or network-based. The host-based deployments usually focus on tracking system calls, on access to local logs. They watch for file system modifications. But the problem is that they are inherently monitored and managed at the end node on the host computer. So they're monitored and managed by individual cloud system users. Well, if that cloud system gets compromised by bad guys, or if it's actually spun up by a bad guy, they're obviously not going to want to play along with our intrusion detection system. They might disable it. They might have it report back false data. For network-based intrusion detection systems, they traditionally monitor traffic. They look at the contents of individual packets. Historically, they've shown limited effectiveness against insider attacks. They're much more effective in watching for externally based attacks coming in. Another problem with network-based intrusion detection systems in cloud environments particularly is that they're less effective due to multi-tenancy, because we've got to segment up these virtual networks to give network isolation to different customers in a multi-tenant environment. Network intrusion systems aren't going to be able to see across those various network environments very effectively. So they're going to be much less effective in a multi-tenant environment. Another issue for us is that it can be hard to identify what are the indicators of compromise that we actually need to detect in these environments. So Daigle and others in 2011 looked at a solution for distributed intrusion detection systems for the cloud. Their approach was to have each virtual machine in the environment host a mini intrusion detection system. And each of those systems would report back to a central controller. So it averts the concern of load imposed by running an intrusion detection system by running lots of these mini intrusion detection systems distributed across the entire virtualized environment. One problem with that is that you need clients for each version of operating system in the environment. So all of the available Windows versions, all of the available Linux versions, for example. The controller would collect this data and store the pertinent data in cloud logs for further analysis. Those logs would be fed to a neural network-based knowledge base that looks for individual users' activity patterns. So relies on pattern matching. It's looking for brute force and access right violations, brute force attacks against other systems and access rights violations. A different approach was proposed by Nikolai and Wang in 2014. It examines system metrics of virtual machines directly from the hypervisor layer to seek patterns of misuse. So it relies on performance signatures of individual virtual machines. The attractive part of this is that it's anomaly detection from outside of the virtual machine environment. So it would not be susceptible to spoofing or attack from virtual machines that had been compromised within that environment. So this effectively provides an IDS framework for cloud environments. It was shown to be 100% effective in detecting two different forms of denial of service attacks which were tested. Since the metrics are collected outside of the virtual machines, this approach is also operating system agnostic, so you wouldn't require customized clients to be written and run for each flavor of operating system. So here's a graphical representation of that environment. So the small circles are the individual virtual machines that are running on a hypervisor server, and these endpoints exist outside of that hypervisor server, and they're collecting data from those hypervisors and passing that information up to a controller. That controller then aggregates and analyzes that data and provides it out to a notification service. So you can see, because the endpoints and the controller are located outside of the hypervisor environment, they're not susceptible to direct attack by those virtual machines. The controller node is a service that resides within the hypervisor environment instead of within the VM environment. It collects and analyzes data in near real time. The way that they achieve this near real time reporting is through a sliding window approach. They use a 10-second window to aggregate CPU utilization numbers, block read and write statistics for memory access statistics, and then they look at network traffic by analyzing the number of packets sent and received. Any behavior that is considered anomalous then triggers a 3-second window that's populated with this anomalous activity every 3 seconds. If it sees 3 occurrences of this anomalous behavior, then it's labeled as a potential attack and compared to known attack patterns. For the purposes of this experiment, unrecognized patterns were ignored. The prototype used IBM InfoSphere Streams product. It was implemented using the IBM Streams Processing Language, or SPL, and it listens on UDP sockets, so it doesn't have the additional overhead of a stateful TCP socket. So in this scenario, the endpoints may be agents on each of those hypervisor physical systems, or it may just be API calls to the hypervisor itself. It would work either way. And then these agents or these API calls would gather and format the data and then send it on to a controller node. On the controller node, a Python script gathers the CPU, the memory access, that block device information, and network metrics by using the libvirt API from that IBM product that we mentioned. It samples every second, and it sends the data in comma-separated value format to the controller node, again using UDP. It resides outside of the virtual machines, so it cannot be controlled or manipulated by cloud users or individual compromised virtual machines in that environment. The notification service provides alerts to external users. They can be visualized in a table or written out to a file for long-term storage. They can also provide log file updates. That output then could be rolled into log file updates, as we said, or into email notifications, or it could be input into another intrusion detection system or a SIEM product, a security event incident management product, like ArcSight or SecureView, for example. So the researchers built their test environment on a Eucalyptus instance. That Eucalyptus instance contained a cloud controller, a Walrus server, a cluster controller, a storage controller, and then node controllers. The Walrus, cluster, and storage controller all resided on a single server, but those could each be stood up on an individual server, for example, to give you much greater capacity. So how did they run the experiment? Well, first they simulated workload, and then they simulated attacks. To simulate the workload, they did 3 runs, conducted each of those runs 3 times. In the first run, they performed different sized reads and writes at intervals of 2 to 5 seconds. In the second run, they did 5 concurrent user accesses. They simulated 5 concurrent users accessing the virtual machine's HTTP server. In the third run, they simulated 10 concurrent users accessing the virtual machine's web server. And then in the simulated attacks, they simulated 2 different forms of denial of service attacks. They did an HTTP flood, and they did a SYN flood. The HTTP flood they launched from outside the cloud environment using DOSHTTP from a Windows 7 machine. They instantiated 500 sockets to issue 10,000 requests. In the second attack, the SYN flood attack, they used hping3 to create a SYN flood from within a virtual machine to attack another virtual machine in the same cloud. They relied on manual observation of patterns during the simulated denial of service attacks to create signatures. The goals of those signatures were to reduce false positives, to determine if they were able to detect all valid attacks, and to properly classify those attacks. The signatures were composed of the packet transfers, the packet receipts, the block device read request, so that memory access request, the block device write request, and CPU utilization. And then again, they did this for 0, for 5, and for 15 concurrent users. The signatures that they developed looked like this. For the HTTP DOS attack, they detected positive on the CPU utilization, they false for read and write, but positive for receipt and transmission of network packets. And for the SYN flood attack, they saw CPU utilization go up. They didn't see a change in the read activity, but they did see a change in the write activity. They didn't see a change in the receipt activity, but they did see a change in the transmit activity. And obviously that SYN flood data is from the attacker's perspective. So they did 3 test runs, the denial of service against the virtual machine, the denial of service from the virtual machine, and then no attack to establish a baseline. They conducted these experiments over 45 minutes, 15 minutes with no users, 15 minutes with 5 concurrent users, and 15 minutes with 10 concurrent users. The attacks were issued 3 times during each condition for a total of 9 runs. And then based on the data from those 9 runs, they came up with these accuracy statistics. For the denial of service attack against a virtual machine, they had a less than 1% false positive rate. They had a 0% false negative rate, and they had 0% misclassifications. For denial of service from one virtual machine against another, they had a 1.4% false positive rate, a 0% false negative rate, and a 0% misclassification rate. And then for no attacks, they had 0 false positives, 0 false negatives. Obviously, false negatives and misclassifications wouldn't apply to the no attack scenario. So the conclusions that we can draw is that this HCIDS, hypervisor-based cloud intrusion detection approach, provides for greater accuracy and greater confidence than traditional or alternative cloud IDS deployments that have been proposed. And they give us results that are comparable to traditional IDS products. It addresses the shortcomings of some of the predecessors. As we said, there's no per host agent, so we don't have to have different versions of the agent for each potential different version of operating system that might be running in our environment. More importantly, there's no requirement for cooperation from the cloud user. It takes the load off of the hypervisor server, which would be important in medium to large enterprises where you've got lots of contention for those resources potentially. And it's a far less complex topology, so we can have a greater degree of confidence in our results, and it'll be much simpler to troubleshoot any problems that we encounter. And then in summation, here's the references that were used in the development of this presentation. Thank you for your attention, and see you in presentation 2.